hydration of an alkene via oxymercuration, demercuration. This is the product we want. Here's mercuric acetate. It's mercury bonded to acetate twice. When it splits apart, it creates this ion. This is the one we care about. This ion, the electrons of this double bond, there's a lot of electron density here. It's going to be attracted to a positive charge, and then these electrons are going to be distributed to each one of these carbons, creating this system right here, where we still have this positive charge, and the double bond's broken apart. Basically, one electron of each one of these carbons, instead of bonding to each other, now they're sharing these electrons with the mercury, so that mercury still maintains that positive charge. So next, water is going to act as a nucleophile on this organic metal system, and it's going to add in a way to give Markovnikov orientation. Now, it's slightly different than the acid catalyzed hydration. We'll have a look at why. So here I drew an example where there are some hydrogens and then there's a CH3 group. So one of these is more substituted than the other. If they weren't substituted, like this one and the continuing examples, I didn't bother putting anything on there. But just hypothetically, if it was more substituted. If it's not substituted, it doesn't matter which one it gets added to. But here, since it is, we've always got to go back and think about what organic chemistry is. Organic chemistry is just an endless battle for electrons, a massive tussle for electrons. So we've got to look at it from the electron's perspective. So here, this carbon is bonded to the mercury ion, which is strongly positive, and two hydrogens. Carbon is stronger at drawing electrons than hydrogen. Here, this carbon is bonded to the same mercury, a hydrogen as well, but also to a CH3 in this example. And carbon is better at attracting electrons to itself than hydrogen. So which one of these two electrons will be more positive? The one on the right, because this one has only two hydrogens to compete against. This one has one hydrogen and a carbon. Carbon's better at withdrawing electrons, so this one will be slightly more positive than this one. In the acid catalyzed hydration, what's added is a proton. A proton is looking for electrons, so it adds to this one instead to create Markovnikov orientation. And then when the other thing comes by, whatever it may be, bromine, water, it still adds to this carbocation that would be here, if this were the acid catalyzed hydration. Here, it's kind of the opposite. We have a nucleophile, and it goes here first because it's more positive. So we get this water added. Also, it's important to note the orientation which it adds in. Since both of these are on the same plane, the water attacks from the back side, so one of these will be pointing up and the other will be pointing down from a stereochemistry point of view. Water will take away one of these protons and then leave the alcohol. So this is the mercuration part. Now the demercuration is the final step. We use a boron compound. It removes this mercury, leaves a hydrogen. They're anti from each other, like this. If we were to draw one of these projections, right, we have hydrogen, the alcohol down here, and then whatever's over there. And it would be in Markovnikov orientation. So this is an alternative to acid catalyzed hydration in situations where this would be more efficient, or the other ways it's just not good from a compound perspective. It doesn't work well in strong acids.